Bismillah Rahman Rahim and Assalamu alaikum. This is Faryal Javed, roll number 21TE07 from Telecommunication Engineering Department, UG Texela. So today I am going to solve lab manual 8 of digital signal processing, that is moving average filter, that is FIR filters Fourier transform design method. Moving towards lab objective of today's lab, that is implementation and analysis of moving average filter, the implementation and analysis of finite impulse response filter Fourier transform design method. So the task one of today's lab is define filter. Then the part B is types of filter. What are the time domain parameters for a filter? What are the frequency domain parameters for a filter? And discuss the role of low pass filter for our filter design. Now the definition of filter is a filter is a device or a circuit that allow a certain frequency or a range of frequencies to pass through while attenuating others. It can be used to modify signals by blocking unwanted frequencies or isolating specific frequency components. Then the types of filters can be categorized into different types based on their frequency response characteristics. It can be a low pass filter, a high pass filter, band stop filter, etc. The band low pass filter basically allow frequencies below certain cutoff frequencies. The high pass allow frequencies above certain cutoffs. Then the band pass filter passes frequencies within a certain ranges or band of frequencies. Then the band stop filters attenuates frequencies within a certain band. Then the time domain parameters for a filters. The time domain parameter described how a filter behaves in the time domain, specifically relating to its impulse response and step response. Then the impulse response describes the output of a filter when an impulse is applied as an input. The step response describes the output of a filter when a step function is applied as an input. The rise time and is the time taken for the output of filter to rise from a specific low value to a specific high value in a response to a step input. Then the part D is what are the frequency domain parameters for a filter. The frequency domain parameter described how a filter behaves in terms of its frequency responses characteristic. Common frequency domain parameters include cutoff frequencies, bandwidth, attenuation, selectivity or Q factor, and a role. Moving towards the part E, that is discuss the role of low pass filter for a filtering designing. Basically, a low pass filter is a fundamental type of filter that allow frequencies below a certain cutoff frequencies to pass through while attenuating frequencies above this cutoff. This low pass filter is commonly used in filter design for a several processing, that is signal conditioning, anti-aliasing, the frequency separation. In filter design, the characteristic of a low pass filter such as its cutoff frequency, the slope, and transition bandwidth are crucial parameters that determine its effectiveness in achieving that described signal filtered objectives. Going toward task 2 of today's lab, that is plot the signal in time and frequency domain along with its magnitude response. We have x1 to 40 is equals to 0, and then the rest of them are given below. Then the part B is apply the 3 tab symmetry around moving average filter on a signal x noise and observe the time and frequency domain parameters. Then we'll have the part C and D. Move towards the part A. The output to the part A of today's lab is as shown. So in this code, we generate a signal where a portion of a sample is set to 1 and the rest is 0, introducing a noise to create a noisy version x noise by adding a random noise zero point 0.5 into random size of x to x. And then we'll have the time domain analysis, plot the original signal and the noisy signal in the time domain using MATLAB stem function, implement moving average filters of different tap lengths. Here is the original signal, that is our noisy signal. Moving towards the task 2 of this lab, that is apply a 3 tab symmetry around moving average filter on signal x noise and observe the time and frequency domain. So the different tab, we use a different tab length, that is 3 11 25 to smooth out the noisy signal x, and visualizing the filtered signal and time domain to observe the noise reduction and signal smoothing effects. Use the frequency function in MATLAB to analyze and plot frequency responses of each moving average filter, that is starting with the first 3 tab filter. Here is the output to our moving 3 tab filter. Then we'll have the task C, that is apply 11 tap symmetry around moving average and then apply 25 tap and observe the time and frequency domain parameters. So after this we apply the 11 tap filters. So the finding the regarding the performing and characteristic of moving average filter with varying tap length in signal processing applications reflect on the trade-offs between noise reduction and signal distortion based on the filter tap length and frequency responses. Now to 25 tap filters. By following these steps and analysis, we can gain insight into a signal processing techniques using moving average filters and their impact on signal quality in both time and frequency domain. Adjustment can be made on the tap lengths. So, the task 3 of this lab is repeat example 7.2 with 7, 17, 51, and 101 tap. Observe the frequency domain parameters. And here is the example 7.2, that is calculate the filter coefficient for a 3 tap FIR low pass filter with a cutoff frequency of 800 and sampling rate of 8000 Hz using a Fourier transform method. Determine the transfer function and difference equation of designed FIR system and then compute and plot the magnitude frequency responses. Now the output to task 3 part A is this. So we define the sampling rate FFS and the desired cutoff frequencies using the FIR one function. We design FIR low pass filter with different tap lengths and plot their magnitude frequency responses. So here is the original signal, then we'll have the filtered signal using 3 tab moving average filter, and then we'll have the FIR low pass filter analysis. That is, this is basically the analysis of the frequency domains. Moving towards the part B of lab, that is apply the filter made in part A to signal X. Observe the change for a signal in time and frequency domain while varying number of coefficient of the filters. And here is the output. In the part B, we generate a signal by combining sinusoid components at specific frequencies for each tap length. From part A, we design the corresponding FIR low pass filter and we apply each filter to signal X using the filter function and plot the resulting filtered signal Y filtered in the time domain. Then moving toward task 4 of today's lab, that is repeat example 7.3 with 7, 17, 51, and 101 tap. Observe the frequency time domain and apply the filter made with in part A to the signal X. Observe the change in signal. And the output to this is as given. So here we have defined the sampling rate and we use different tap length and band pass filter specifications. So we calculate the cutoff frequencies for each tap length, design an FIR bandpass filter using FIR1 function, and we computed and plot the magnitude frequency responses of each filter using frequency Z function, and displaying the response in decibel against the frequency output. So this plot showing the magnitude frequency response of FIR bandpass filters with different tap lengths, allowing analysis of their frequency domain characteristics. So the part B of this task is to generate a signal by combining sinusoidal component specified frequencies. So here we this plot shows that the original signal and the filtered signal after applying FIR bandpass filter with different tap length, analysis of how filter modifies signal in time domain, and demonstrating the effects of different filter lengths on the signal components. So this is it from my side. Thank you. Allah Hafiz.